Thin-walled pressure vessels. Let's look at some of the learning outcomes. Understand thin-walled pressure vessels using radius to thickness ratio and solve thin-walled pressure vessel problems using the formulas stress 1 is equal to PR over T and stress 2 is equal to PR over 2T. For thin-walled vessels, the stress distribution does not vary significantly throughout the thickness of the wall, so we assume that the stresses to be uniform or constant in the wall. This occurs for vessels where the inner radius r over the thickness t is greater or equal to 10. Take a look at this cylindrical vessel. Consider an element of the vessel that's subjected to the normal stress tension, stress 1 in the circumferential or hoop direction, and subjected to a normal stress tension, stress 2 in the longitudinal direction. Let's look at stress 1 or our hoop tension. First, we will section the vessel to remove a hoop of unit dy. Then we section the hoop across the diameter. We can see that the uniform hoop stress is acting on the vessel's walls, while pressure is acting on the gas. Now we can solve for hoop stress by using the summation of forces in the x direction. Rearranging for hoop stress, we get the equation hoop stress is equal to PR over T. Now let's look at stress 2, which is our longitudinal tension. We will section the vessel across the diameter. Longitudinal tension acts over the vessel cross-section area, A2, where A2 is equal to 2 pi r, which is the circumference of a circle, multiplied by T, which is the thickness of the vessel. P acts over the vessel inside circular area AP, where AP is equal to pi r squared. For equilibrium, we will once again take the summation of forces in the x direction and rearrange for longitudinal tension. We get the equation longitudinal tension is equal to PR over 2T. Notice that it is half as large as hoop tension. Let's take a look at this example. The cap on a cylindrical tank is bolted to the tank along the flanges. The tank has an inner diameter of 1.5 meters and a wall thickness of 18 millimeters. If the largest normal stress is not to exceed 150 MPa, determine the maximum pressure that the tank can sustain. To solve this question, know that the largest normal stress occurs in the hoop direction for a cylindrical vessel. We turned the diameter into the radius, which is 0.75 meters, and now we can use the equation stress is equal to PR over T to solve for P, which is the internal pressure developed by the gas. We'll substitute our values in and rearrange for P, and we get an answer of 3.6 MPa. Therefore, the maximum pressure the tank can sustain is 3.6 MPa. Summarize what we learned. A pressure vessel is considered to have a thin wall provided that the ratio between radius and thickness is above or equal to 10. Circumferential or hoop stress in a cylindrical vessel is stress is equal to PR over T, and stress is half as large in the longitudinal stress. Stress 2 is equal to PR over 2T.